Okay, in this lesson, we're going to talk about what can dissolve into solutions and what cannot dissolve, okay? In the world of solvation or dissolving or making solutions, there's a phrase that's often called out that says, like dissolves like, okay? And it's a really easy phrase, but you have to know what it pertains to. So when we say like dissolves like, we're pertaining to polarity of molecules, okay? So earlier in this year, we learned about what molecules are polar, what molecules are nonpolar, and we also talked about how ionic compounds aren't either really, but really ionic compounds are an extreme case of polarity. So they're more like a polar molecule than they would be a nonpolar molecule, okay? So when it comes to dissolving, like what can dissolve something else, you have to have similar polarities of those substances, okay? Which means if you are a polar molecule, like water is an extremely polar molecule. We talked about that a lot this year. It can dissolve other polar molecules. It also can dissolve most ionic compounds, not all of them, but most of them. And we'll talk about why in a second, all right? Water, being a very polar molecule, cannot dissolve nonpolar molecules, okay? So there's a separation there. We've used earlier in this year kind of the oil and water mixture, talking about some different things. That's a very good example of that, where oil is a nonpolar substance, so it can't dissolve or mix with water, which is very polar, okay? So that idea of like dissolve likes is aligning with polarities, all right? Now let's talk a little bit more about why some ionic compounds can't dissolve in water, all right? If you recall, we've talked about how ionic compounds get their strength from their crystal lattice and how the crystalline structure actually gives them kind of like a locking pattern that holds everything in place, okay? For water molecules, or any solvent really, to disrupt that crystal lattice, they have to have enough energy or enough ability to pull that lattice apart on its edges, okay? For some ionic compounds, that lattice energy is too great, okay? So for some ionic compounds, it just takes too much energy to pull them apart so they don't dissolve in comparison to, say, like water as a solvent. So water being the solvent, if it isn't strong enough, if its dipole to ion interaction isn't strong enough to break apart the crystal lattice, it just won't happen, okay? And as a result, those ionic compounds will not dissolve in water. Now, the easiest way to know which is we go back to our solubility rules we've established earlier in this year. They're on the back of your periodic tables, or look up solubility charts, okay? For polar molecules, we can assume that anything that's a polar molecule will dissolve into water or other polar molecules. We can also assume that anything that is nonpolar will not dissolve into polar molecules. Flipping that around, if you are a nonpolar solvent, something like hexane, we talked about before as a nonpolar solvent, that could dissolve other nonpolar things, okay? But ionic compounds, we have to check our solubility rules, okay? We treat them like polar with a checking mechanism of, okay, we think ionic compounds can dissolve in water, but we have to check to see if they can or cannot, okay? Now, that being said, there's a lot of cases in our world where we have nonpolar things mixed with polar things, okay? Think about like oils and greases and gasoline and those kind of things. We can clean them up, and usually we use water as a base for that. So water is a polar molecule, and it somehow is being able to attach itself and to dissolve nonpolar things like oils and greases and grimes and that kind of stuff, okay? So if we wanted to force a nonpolar substance and a polar/ionic substance to mix, we have to find a way to do that, okay? And to do that, we need a special kind of molecule. That special kind of molecule is called a surfactant, okay? Now, surfactants are kind of unique in the fact that they are very long chain molecules. And because of this really long chain of hydrocarbons on it, one side of that long molecule essentially acts like it's nonpolar. The other side, way over here, acts as it's being polar or almost ionic to that nature, okay? We say this nonpolar end is hydrophobic, meaning it's scared of or does not like water. We say that this polar end is hydrophilic, meaning it likes or wants to be by water, okay? So this polar end can attach to water molecules. This nonpolar end can attach to anything that's nonpolar, and it kind of provides like a link or a bridge between the two. So that's kind of how it modifies that like dissolves like scenario, okay? Surfactants are used all over. All of our soaps, all of our cleaning materials are surfactants of some way, shape, or form because they allow us to attach water to things that normally would not be able to dissolve. That's why we need soap when we wash our hands and our clothes and that kind of stuff, okay? We also have surfactants that act in the food industry, okay? When we have that, we call those emulsifiers, okay? So if you're adding things like eggs or other ingredients that help bind the food together, a lot of times those things are surfactants, which then allow the fats in the foods to bind with water and be able to bake or cook whatever your food is, okay? This little video kind of shows you this process, how it works.
Surfactant molecules exist in aqueous solution as micelles, clusters of surfactant molecules. The long nonpolar chains of the surfactant molecules are pointed inward, and the polar charged end groups point outward into the water. In solution, water molecules interact with the polar negatively charged ends of the surfactant molecules and with the sodium cations that provide charge balance. When a microscopic oil particle on an item of clothing is exposed to this solution and there is agitation, the surfactant molecules become embedded in the oil droplet through the hydrophobic, oil-loving hydrocarbon chain part of the molecules.
Wow, isn't that a whole mouthful of words? Okay, so basically what she's saying is that the nonpolar ends stick themselves into the oil because they like each other, because they're the same. And the polar ends stay out where they're still attached to the water.
As more and more surfactant molecules become embedded in the oil droplet, it is lifted from the surface of the clothing. This process occurs because the polar charged ends of the surfactant molecules interact strongly with the surrounding water.
Okay, so kind of a reiteration of what we talked about already down here, but you got a chance to see how the nonpolar ends embed themselves into oils or other nonpolar molecules that might exist there, okay? So that's kind of how surfactants work. They're kind of a key thing because they link our worlds together between polar and nonpolar, all right? Now, in our next video, we will discuss how electrical conduction plays a role in this. Thank you.